Okay, so hopefully, before you started playing the video, you took a few minutes to work the drill. So you were just evaluating the functions there. So we're just going to let these answers pop up. You can check your responses. You can type that in your calculator. You could have done it by hand. You could have done it by head. It's up to you, however you wanted to solve that. Today what we're going to do is we're going to look at the rules of adding and subtracting, multiplying and dividing functions to perform arithmetic operations on them. And we're also going to talk about function compositions. Okay, and we're also going to talk about inverse functions, I believe. So basically when you do the algebra of functions, when you're adding and subtracting or doing arithmetic on functions, you basically evaluate the function and then do the mathematical operation. So if I want to add two functions together, I'm just going to do f plus g, and I'm going to add those together. If I wanted to add those f times g, I would multiply those together. The only problem comes into effect when you have division, and in division then you have to say, okay, I can divide there, but my denominator can't be 0. So that's something you have to take into consideration. All right, so it says, first of all, that f of x is 3x squared plus 2x plus 1. G of x is 5x minus 2. So we're just going to add those together. So I substituted them in using parentheses because that's just good math practices. And then what I want to do is I want to add like terms. I have nothing that's going to change what's inside the parentheses, so I can just add those. So when I add my like terms, my x squared had nothing to be combined with. 5x and 2x had 7x, and 1 and negative 2 was negative 1. Boom. Next we're subtracting, so this time it says to do instead of f minus g, we're doing g minus x. So we're going to do 5x minus 2 minus the quantity of 3x squared minus 2x. Plus 2x plus 1. So when we distribute the negative, that's going to change all the signs in the second set of parentheses. So we have a negative 3x squared, a negative 2x, and a negative 1. And now we combine like terms. So we can see that the 3x squared, again, is the only squared term. We can see that the 2x is negative, and 5x, that's going to give us a positive 3x. And negative 2 and negative 1 gives us a negative 3. And then finally it asks us to evaluate f minus g, but this time of 4. So if we do f minus g, so we would have to calculate what f minus g is. So we'd have 3x squared, then we'd have 2x minus 5x, which would be a negative 3x. Sorry, I forgot what I was doing there. We're just doing f of 4, so evaluate f of 4. So I substitute 4 in for my f function. And that gives me 57. Then I do g of 4, which gives me 18. And then I subtract those. Okay, so we're doing the same thing here. Why don't you pause the video and try these on your own and then come back and check. Hopefully you got those right. If not, talk to one of your neighbors to see how they did it. So the composition of functions is when we actually do f following g of x or f of g of x. So what you're going to do at this place is you're going to take the g function and plug it into the f function. So what we're asked to do here, f of x is 3x plus 2. G of x is 5x minus 7, so we're asked to find both directions. We're supposed to find g following f, or excuse me, f following g, and then g following f. Anytime I see these, I always go ahead and put parentheses. So that I know I'm going to take my g function and plug it into f, and then in the second one I'm going to put my f function into g. So I'm going to do f following g of x, which means f of g of x. So I'm going to take 5x minus 7, substitute that into the f function. So I have 3 parentheses 5x minus 7, close the parentheses, plus 2. And I evaluate that. So I distribute my 3 and then combine like terms. So I have 15x minus 19. Now I'm going to do the reverse. So I really am checking this to see if it matters the order that I put the operations in. Like, can I do it in a different order? Does it matter if f comes first, or does it matter if g comes first? So we're going to check that out. So I'm now going to take 3x plus 2 and plug it in for x in 5x minus 7. So 3x plus 2 goes in for x. So I have 5 times 3x plus 2 and then minus 7. And you'll see that they are different. So what we can learn from this is that the order we do the composition matters. The order we do the composition matters. So does f of g of x equal g of f of x? And the answer is no. No, it does not. Okay? The order matters when we do composition. So we're going to do the same thing, okay, here, but this time we have squareds. Doesn't change anything, we just have to expand more. So now we have to do 2x squared plus 1 squared. So that's 2x squared plus 1 times 2x squared plus 1. So when I multiply that, I get 4x to the 4th plus 4x squared plus 1. So that gives me 4x to the 4th plus 4x squared minus 3. And that's my first composition. So now I'm going to do the reverse, and I'm going to put x squared minus 4 in for 2 quantity x squared plus 1. So I'll square the x squared minus 4, and then I'll distribute the 2. You got to do order of operations, so you have to do the exponent first. So once we've got that squared, then we can distribute our 2 and combine like terms. And again, do they equal the same thing? And the answer is no. The order that you do composition matters. Composition is not a commutative function. So the order of composition matters. So the last thing we need to talk about are inverse functions. F is a function, and inverse to f is a function that interchanges all ordered pairs. The inverse of f of x is denoted by f to the negative 1 of x. Basically what happens is, if the first ordered pairs were x, y, then in the inverse, okay, so if that's our original function, in the inverse, the functions are going to be yx. So in order to find your inverse, you're going to switch your x's and your y's. A function has an inverse function if that function is a one-to-one function. Now that's the only time it can be an inverse function, is if it has a one-to-one function. So in other words, we said a function is each x has only one y. Well, in a one-to-one function, each y has only one x. So not only are the x's only used once, the y's are also only used once as well. If two functions are inverses of one another, then the x values and the y values are interchanged. And a function is one-to-one if it passes the horizontal line test. So that means that it'll pass a horizontal line, will pass through the function no more than 1 point at a time. So to verify that two functions are inverses, what we do is we do their composition. So we do f following the inverse of x, and then we do the inverse following f of x. Additionally, the graphs of the inverse functions are reflected in the line y equals x. So if we draw a line y equals x, the inverses will be reflected over that line. So if you're looking at a graph, there's a way to decide it. And if you're looking at a function, there's a way to determine it if you're looking at it in function notation. So here we have two functions, f of x and g of x. So I'm going to graph x plus 5. So I started at the y-intercept of 5. I went up 1, right 1, up 1, right 1, up 1, right 1. Then we did x equal x minus 5. So that means we went down 5, up 1, right 1. And if I were able to fold this screen on the line y equals x, these lines would be on top of each other. Now, to show that they are algebraically, I would have to compose them. If I do that composition, it should equal x. So the first time I do it, f composed with g, so I put the g function into the f function, I get x. Second time I do it, I put the f function into the g function, and I get x. Since both of those functions, when they're composed together, equals x, they are inverses. You have to check both ways. So here's another example. So if we graph 2x minus 7, we start down at negative 7. We go up 2, right 1, up 2, right 1. Then if we graph y equals x plus 7 all divided by 2, we start at 3.5, and we go up 1, right 2, up 1, right 2. Boom. Okay, and then we can see if we put the line y equals x in, and we're able to fold on that, that those two graphs would be on top of each other. The easier way to do it is probably to check it algebraically, though, so we substitute those values in. 2 times that quantity just gives us x plus 7, and x plus 7 minus 7 is just x. So that works. The next equation, we take 2x plus 7 and substitute it in. 2x minus 7 plus 7 is just 2x. 2x divided by 2 is just x. So these are, in fact, inverses. Now, if they ask you to come up with the inverse, which is something they could ask you to do, what you want to be able to do is to solve for the inverse. So the first thing you do is you replace f of x with y. And then after you've done that, you switch your x and y's. And now you solve your equation for y. That should be the inverse. So then you replace your y with f of negative x, and that is the inverse of the original function. Same thing here. Start by replacing f of x with y. Even though it said g of x, we're still going to make it say y equals. Interchange our x and y, so instead of y equals x over 12, it's x equals y over 12. We solve for y, so we multiply 12 on both sides. And that's our inverse. So we write that as, instead of f inverse, this is going to be g inverse equals 12x. Same thing here. Rewrite h of x as y equals. Switch your x's and your y's. Solve for y, so multiply both sides by 4, then subtract 5, then divide by 3. And that's your inverse. Let you try this one. Okay, so now what you're going to have to do is go to my math lab, and there should be an assignment there for you to complete entitled Composites and Inverses. Thanks.